with reference to ship's side valves. A. State why grey cast iron is not a suitable material. B. State with reasons 3 suitable materials. A. Why grey cast iron is not a suitable material for ship's side valves. Grey cast iron is not a suitable material for several reasons. It is brittle. Grey cast iron is brittle, which means it is more likely to crack or break under stress than other materials. This is a major concern for ship's side valves, which are subjected to high stresses from waves and currents. It has poor corrosion resistance. Grey cast iron is not very resistant to corrosion, especially in seawater. This means that it is likely to rust and deteriorate over time, which could lead to leaks and failures. It is weak in tension. Grey cast iron is weak in tension, which means that it is not able to withstand pulling forces very well. This is important for ship's side valves, which need to be able to withstand the pulling forces of the piping system. Part B. 3 suitable materials for ship's side valves with reasons. There are a number of materials that are suitable for ship's side valves, but 3 of the most common are ductile iron. Ductile iron is a type of cast iron that has been treated with magnesium or cerium to make it more ductile and less brittle than grey cast iron. This makes it a much more suitable material for ship's side valves. Or bronze. Bronze is an alloy of copper and tin, or copper and aluminium, that is strong, corrosion resistant and ductile. This makes it an excellent choice for ship's side valves, especially in applications where seawater is present. Stainless steel. Stainless steel is a steel alloy that is resistant to corrosion and has good mechanical properties. It is a more expensive option than ductile iron or bronze, but it can be a good choice for ship's side valves that need to be particularly strong and durable. Explain how the properties of steel are modified by its carbon content. Explain each of the following terms. 1. Annealing. 2. Normalizing. 3. Hardness. Steel properties and carbon content. The carbon content in steel significantly influences its properties in several ways. Strength and hardness. As the carbon content increases, the strength and hardness of steel also increases. This is because carbon atoms form strong bonds with iron atoms, hindering dislocation movement and making the material more resistant to deformation. Ductility and malleability. Conversely, higher carbon content reduces the ductility and malleability of steel. The tangled crystal structure caused by carbon atoms makes it more difficult to bend or shape the material without cracking. Weldability. High carbon steel becomes less weldable due to increased susceptibility to cracking around the weld zone. Careful control of heat and filler materials is necessary during welding. Machinability. Low carbon steel is easier to machine due to its softer nature. As carbon content increases, machining becomes more challenging and requires specialized tools. Corrosion resistance. Generally, higher carbon content reduces the corrosion resistance of steel. However, certain high chromium stainless steels with moderate carbon content offer excellent corrosion resistance. Therefore, the optimal carbon content for steel depends on the desired properties for a specific application. A balance between strength, ductility, weldability, and other characteristics is often sought based on the intended use. Explaining heat treatment terms. 1. Annealing. Annealing is a heat treatment process that softens a work-hardened or quenched steel by relieving internal stresses and promoting grain growth. This increases ductility and malleability while reducing strength and hardness. It typically involves heating the steel to a specific temperature above its recrystallization temperature and then slowly cooling it. Annealing is used to improve formability, relieve welding stresses, and prepare steel for further processing. 2. Normalizing. Normalizing is a heat treatment process similar to annealing, but involves heating the steel to a higher temperature above its critical temperature and then cooling it in air. This refines the grain structure, resulting in a balance between strength and ductility compared to annealing. Normalizing is often used for forging and casting processes to improve mechanical properties and machinability. 3. Hardening. Hardening is a heat treatment process that involves austenitizing, heating above the critical temperature of steel, followed by rapid quenching or cooling. This rapid cooling traps carbon atoms in the austenitic lattice structure, forming a metastable phase called martensite. Martensite is very hard and brittle, significantly increasing the steel's strength and hardness. However, it becomes more brittle and susceptible to cracking. Hardening is often followed by tempering to improve toughness and reduce internal stresses without significantly sacrificing strength. 3. Explain each of the following terms. A. Ductile cast iron. B. Tensile stress. C. Work hardening. D. Shear stress. E. Young's modulus. A. Ductile cast iron. Ductile cast iron is a type of cast iron with improved ductility and toughness compared to traditional cast iron. This is achieved by adding a small amount of magnesium or cerium during the manufacturing process, which changes the graphite microstructure from flakes to spheroids. This results in a material that can deform considerably before breaking, unlike the brittle nature of traditional cast iron. Ductile cast iron is used in various applications like pipes, automotive components, and machine parts requiring strength and some flexibility. B. Tensile stress. Tensile stress is a pulling force acting on a material, trying to elongate it in the direction of the force. Imagine pulling a rope. The rope experiences tensile stress, stretching as you pull harder. It is one of the basic types of stress encountered in materials, alongside compressive stress, pushing, and shear stress, distortion. C. Work hardening. Work hardening, also known as strain hardening, is a phenomenon where a material's strength and hardness increase as it undergoes plastic deformation, permanent shape change, due to external forces. Imagine repeatedly bending a metal wire. It becomes progressively harder to bend further as the work hardens. This property is utilized in metalworking processes like cold forging and wire drawing. Shear stress. Shear stress is a force that acts to slide or distort one part of a material relative to another along a parallel plane. Picture pushing two bricks against each other. They experience shear stress at the contact point, potentially causing them to slide and deform. It is another fundamental type of stress along tensile and compressive stress, and it plays a crucial role in phenomena like friction and material failure. E. Young's modulus. Young's modulus, also known as the elastic modulus, measures the stiffness of a material within its elastic range where deformation is temporary. It quantifies the relationship between stress and strain within this region. A higher Young's modulus indicates a stiffer material that requires more force to deform a given amount. Think of a steel beam compared to a rubber band. The steel has a much higher Young's modulus, making it much stiffer. With reference to gas metal arc welding, MIG, of mild steel. A. Describe the process. B. Explain, with reasons, the surface preparation required. C. List 3 advantages and 1 limitation. A. The MIG welding process. MIG welding, also known as metal inert gas welding, is a semi-automatic welding process that joins metals using a continuously fed consumable solid wire electrode and an inert shielding gas. Here's a breakdown of the steps. 1. Preparation. Clean the weld area thoroughly to remove dirt, grease, rust, paint, and any other contaminants that can weaken the weld and introduce impurities. 2. Setup. Choose the appropriate wire and inert gas. e.g. argon or argon-CO2 mix, based on the material and desired weld characteristics. Install the wire and gas cylinder. Set the wire feed speed and welding current according to the material thickness. 3. Welding. Hold the welding torch at the appropriate angle and distance from the joint. As you trigger the welding run, the wire feeds continuously and an arc forms between the wire tip and the metal, melting both materials. The shielding gas protects the molten metal from atmospheric contamination. 4. Travel speed. Move the torch steadily along the joint seam at a controlled speed, melting and joining the metal while leaving a continuous weld bead. 5. Cleaning. Allow the weld to cool completely and then remove any slag residue with a chipping hammer or wire brush. B. Surface preparation and its importance. Proper surface preparation is crucial for achieving strong and high-quality MIG welds in mild steel for several reasons. Contaminants. Dirt, grease, rust and paint can all prevent the molten metal from properly bonding with the base metal, leading to weak welds and potential porosity, gas bubbles, within the weld. Oxidation. Rust and oxidation layers create impurities that can affect the weld strength and introduce slag inclusions. Smooth melting. Clean and prepared surfaces offer a better contact surface for the molten metal, allowing for smoother melting and a more consistent weld bead profile. Therefore, thorough cleaning with grinding, wire brushing, or other appropriate methods ensures optimal weld quality and performance. C. Advantages and limitations of MIG welding. Advantages. 1. Versatility. Handles a wide range of materials and thicknesses with ease. 2. High deposition rate. Creates thick and strong welds quickly due to the continuous wire feed. 3. Cleanliness. Inert gas shielding minimizes spatter and fumes compared to other welding processes. Limitation. 1. Wind sensitivity. The shielding gas can be easily affected by wind, requiring shielding devices in outdoor environments for consistent weld quality. MIG welding offers a balance of ease, speed, and quality for mild steel welding, making it a popular choice for various applications. However, its wind sensitivity needs to be considered for outdoor work. Fretting and pitting corrosion. A. With reference to fretting corrosion, 1. Explain the process. 2. State a common cause. 3. State how it is normally detected. B. With reference to pitting corrosion, 1. Explain the term pitting corrosion. 2. State 2 common causes. 3. Explain why it is considered to be dangerous. A. Fretting corrosion. 1. The process. Imagine two surfaces in tight contact, experiencing slight relative movement due to vibration or thermal expansion. The microscopic rubbing and slipping create wear particles which further abrade the surfaces. This combined mechanical wear and oxidation generates a reddish-brown powder and localized pitting known as fretting corrosion. 2. Common cause. Vibration is a common culprit, particularly in components like bearings, gears, and bolted connections. Even seemingly insignificant vibrations can trigger fretting over time, especially when compounded by high pressure or poor lubrication. 3. Detection. Visual inspection can reveal reddish-brown powder or discoloration at contact points. However, early detection often requires non-destructive testing methods like ultrasonic testing or eddy current testing, which can detect subsurface damage before it becomes visible. B. Pitting corrosion. 1. Explanation. Pitting corrosion is not a uniform attack on the metal surface, but rather the formation of isolated deep cavities called pits. These pits can penetrate deep into the material, often invisible to the naked eye, until significant damage has occurred. 2. Common causes. Pitting can be caused by several factors, including chloride ions. These are particularly aggressive towards many materials, particularly stainless steel, and can initiate pitting by breaking down the protective passive layer. Seawater and environments with high salt content are prime culprits. Acidic or alkaline environments. Extreme pH levels can destruct the passive layer and make metals more susceptible to pitting corrosion. This can occur in industrial environments with chemical spills or even in rainwater with acidic pollutants. 2. Danger of pitting corrosion. Pitting's insidious nature lies in its localized attack. The deep, narrow pits can significantly weaken the material, even if the overall surface area affected is small. This can lead to sudden and catastrophic failures, especially in components under high stress, like pressure vessels, aircraft structures. Understanding the mechanisms and detection methods for both fretting and pitting corrosion is crucial for ensuring the structural integrity and safety of components in various applications. Implementing strategies like vibration dampening, lubrication, protective coatings, and regular inspection can significantly mitigate these forms of corrosion and extend the lifespan of the materials. With reference to the production of glass reinforced plastic GRP hulls. A. Describe the process of resin infusion molding for the production of a hull. B. State the advantages of resin infusion molding with respect to traditional methods of construction. C. Explain how this process can virtually eliminate the onset of osmosis in the hull. A. Preparation. The first step is to prepare the mold. This typically involves cleaning and waxing the mold to ensure a smooth finish. Layup. The dry glass fiber reinforcements are then placed in the mold. These reinforcements can be in the form of mats, woven fabric, or unidirectional tapes. Resin infusion. The resin is then infused into the dry glass fibers. This can be done by gravity, but is more common to use a vacuum to draw the resin through the fibers. Curing. Once the resin is infused, the mold is sealed and the resin is allowed to cure. This is typically done at an elevated temperature. Finishing. Once the resin is cured, the part can be removed from the mold and any finishing work can be done. This may include sanding, painting, or adding hardware. Resin infusion moulding has several advantages over traditional methods of GRP hull construction, such as hand layup and spray up. These advantages include higher fibre to resin ratio. Resin infusion moulding typically results in a higher fibre to resin ratio than other methods. This means that the hulls are stronger and lighter. Reduced void content. Resin infusion moulding also reduces the void content in the laminate. Voids are air pockets that can weaken the laminates and make it more susceptible to water absorption. Improved surface finish. Resin infusion moulding typically produces a better surface finish than other methods. This is because the resin is evenly distributed throughout the laminate. Reduced emissions. Resin infusion moulding is a closed mould process, which means there are fewer emissions of volatile organic compounds, VOCs, into the atmosphere. Resin infusion moulding can also virtually eliminate the onset of osmosis in the hull. Osmosis is a process that can cause blisters to form on the surface of the hull. It is caused by the diffusion of water through the hull and into the laminate. Resin infusion moulding creates a denser laminate with fewer voids, which makes it less susceptible to osmosis. Overall, resin infusion moulding is a versatile and efficient process for producing high-quality GRP hulls. It is a good choice for boat builders who are looking for strong, lightweight, and durable hulls. With reference to capacitance probe sensors. A. Describe, with the aid of a sketch, how a capacitance probe produces an output which can be used to measure the liquid level in a tank. B. State 2 different uses of this device on a vessel. C. State 1 disadvantage of this type of probe. A. Capacitance probe operation and sketch. Imagine a tank filled with liquid and within it a slender probe like a metal rod inserted. This is the essence of a capacitance probe sensor, and here's how it works. Look at the sketch. Electrodes. The probe itself acts as one electrode, and the tank wall or other immersed conductor serves as the other. Dielectric constant. The space between the electrodes is filled with the liquid, which acts as a dielectric material with a specific dielectric constant, epsilon. This constant influences the capacitance formed between the electrodes. Capacitance change. As the liquid level rises or falls in the tank, the volume of the dielectric, the liquid, changes. This in turn affects the overall capacitance between the electrodes. Measuring the change. An external device connected to the probe measures this change in capacitance. Level conversion. Using pre-programmed equations and calibration data, the device converts the capacitance value into a corresponding liquid level reading. Key points. The dielectric constant of the liquid significantly impacts the sensor's sensitivity. Capacitance probes are contactless, offering non-invasive level measurement. B. Applications on a vessel. 1. Fuel tank monitoring. Accurately tracking fuel levels in tanks is crucial for fuel management and voyage planning. Capacitance probes provide reliable and continuous level readings, ensuring optimal fuel utilization. 2. Bilge water management. Monitoring bilge water levels is essential for ensuring the vessel's seaworthiness and preventing flooding. Capacitance probes offer accurate level data, triggering alarms or pump activation in case of excessive accumulation. Disadvantages. One potential drawback of capacitance probes is their susceptibility to changes in the dielectric constant of the liquid. Materials like oil or seawater with varying conductivities or contaminants can affect the capacitance readings and require careful calibration or compensation techniques for accurate performance. Remember, capacitance probes offer a valuable tool for liquid level management on vessels, but understanding their operating principles and potential limitations is crucial for their effective implementation. Choosing the right probe type and considering the liquid properties are essential for reliable and accurate level monitoring. With reference to an impeller type flow meter, describe how an output is produced and processed to provide each of the following. A. An analog output in litres per minute. B. A digital output in litres per minute. A. An analog output litres per minute. 1. Impeller rotation. As fluid flows through the meter, the impeller rotates at a speed proportional to the flow rate. The impeller blades are designed to minimize drag and ensure consistent rotation with flow changes. 2. Magnetic coupling. The impeller shaft is coupled to a magnet inside the meter housing. This magnet rotates with the impeller, creating a changing magnetic field around it. 3. Pickup coil. A stationary pickup coil positioned near the rotating magnet senses the changing magnetic field. This induces a voltage signal in the coil whose frequency is directly proportional to the impeller rotation speed and hence the flow rate. 4. Signal conditioning. The induced voltage signal from the pickup coil is typically weak and noisy. Electronic circuitry amplifies and filters the signal to remove noise and ensure a clean, reliable representation of the flow rate. 5. Scaling and calibration. The conditioned signal is then scaled and calibrated based on the meter's specific characteristics. This converts the signal voltage into an analog voltage proportional to the flow rate in litres per minute, LPM. The scaling factor is determined during the meter's calibration process using known flow rates. 6. Analog output. The resulting voltage signal, representing the flow rate in litres per minute, is available as the analog output of the flow meter. This can be directly connected to an analog to digital converter, ADC, for further processing, or used directly in analog control systems. B. Digital output of litres per minute. 1. Signal conditioning. Similar to the analog output, the induced voltage signal from the pickup oil is amplified and filtered. 2. Frequency to digital conversion. Instead of scaling the signal directly, a frequency to digital converter, FDC, is used. This chip measures the frequency of the signal, which is directly proportional to the impeller rotation speed and flow rate. 3. Microprocessor and calculations. The FDC signal output, representing frequency, is fed into a microprocessor within the flow meter. The microprocessor uses the meter's calibration data and internal algorithms to convert the frequency data into a flow rate value in litres per minute, LPM. 4. Digital output. The calculated flow rate in LPM is available as the digital output of the flow meter. This can be displayed on the meter itself, transmitting through serial communication protocols or used for digital control systems. In both cases, the impeller rotation serves as the basis for flow measurement. However, the processing and interpretation of the signal differ, resulting in either an analog voltage or a digital flow rate value as the output. A. Describe, with the aid of a control block diagram, how a governor maintains the speed of a diesel engine driving a generator. B. Describe the reasons for integrating the error signal and the effect it has on the governor fuel rack. The governor in a diesel engine driving a generator maintains the engine speed by regulating the fuel supply based on sense deviations from the desired speed. Here's the control block diagram with its components and functions. Speed sensor measures the actual engine speed, feedback signal. Governor, the controller, compares the measured speed with the desired speed, set point, and calculates the error. Error is the difference between actual and desired speed. Gain amplifies the error signal to adjust the fuel rack position effectively. Fuel rack regulates the amount of fuel delivered to the engine cylinders. Fuel injector injects fuel into the cylinders based on the rack position. Set point represents the desired engine speed, often adjustable based on generator load. Engine load, external disturbance affecting the engine speed, e.g. increased electrical demand. B. Integrating the error signal. Governors often incorporate integral action to improve speed regulation. Reason: constant speed deviations, steady state errors, can occur with proportional, i.e. gain, control alone. The governor might react to the initial error, but may not reach the set point perfectly, especially under varying loads. The effect: integrating the error signal accumulates the error over time, providing a larger correctional signal until the error is eliminated. This helps the governor remember past deviations and adjust the fuel rack further to reach the exact set point even with external disturbances. Impact on the fuel rack. Integrating the error results in a gradual, sustained adjustment of the fuel rack towards the required position. This ensures the engine speed converges to and maintains the desired value, overcoming steady-state errors. In summary, the governor uses a feedback loop with error correction and amplification to regulate the fuel supply and maintain the engine speed despite load changes. Integration improves the system's ability to eliminate steady-state errors and achieve precise speed control.